Okay. Now let's discuss an interesting topic about these connected graphs. Okay. Those are cut vertices and cut edges. It is there in the name itself. Cut vertex. So what do you mean by a cut vertex? So we define a cut vertex for a connected graph. So we say that a vertex is a cut vertex of a connected graph if it disconnects the graph by removal of that vertex. For example, you take a graph of this type. So the vertices are 1, 2, 3, 4, 5, 6 and 7. These are the vertices, right? Now, do we have any cut vertex? It means by removing that vertex, the graph has to be disconnected. Okay, you may ask me one thing. What do you mean by removal of a vertex? Okay, so let me tell you. Here, for example, if I want to remove this vertex 4, you need to remove the incident edges also, like this. So by removing the vertex 4, this is the graph we got. Now, is this graph connected or disconnected? This is disconnected, right? Now, what we get here is, by removal of the vertex 4, we got a disconnected graph. Therefore, we can say that this vertex 4, this is a cut vertex. Okay. So, do we have any other cut vertices here? It means by removal of that vertex, the graph must become disconnected. Suppose if I remove one, uh, is it becomes disconnected? No. All right. Yeah. What are the cut vertices? 2, 3, 4, 5, 6. These are all cut vertices. All right. So these are all cut vertices of this connected graph. Okay. Now let me give you one more example. So let me consider this graph. All right. So is this graph, does it have any cut vertex? It has 5 vertices. So you remove any vertex here. For example, if I remove the vertex, let me name it as 1, 2, 3, 4, 5. So by removal of the vertex 1, what is the graph we are going to get? Removing vertex 1, right? So we will get this graph. From 2 to 3, there is an edge. From 2 to 5, there is an edge. Then to 3, and then to 1 we don't write, because we need to remove all the incident edges to 1, right? So this is the graph we get by the removal of 1. Okay, but it is connected. So this graph does not have any cut vertex. So I can say that there is no cut vertex in this graph. Now I'm going to define vertex connectivity of vertex connectivity of a graph. I mean, the minimum number of vertices needs to be removed so that the graph becomes disconnected. See, in the first example, we have many cut vertices. Alright, you remove any one of these cut vertices, it becomes disconnected. But in the second example, in the star example, there is no cut vertex. Okay, now how many number of vertices you need to remove so that it becomes disconnected? Can you tell me? Minimum number of vertices removed so that this becomes disconnected. The answer is not 1, because by removing one vertex, it is not disconnected because it has no cut vertex. Okay. Yeah, so minimum 2 cut vertices are, needed here, right? For example, if I remove 1 and 5, is it becoming disconnected? Removing 1 and 5. No, it is not, right? Removing 1 and 5, what do you get? You get this one. 2, 4. No, I think it is becoming disconnected, yeah? Removing 1 and 5. 2, 3, and 5. Oh, from 3 to 5 there is an edge, sorry. Right, there is an edge. Why I am taking 5? I am removing 1 and 5. So I need to consider 4. 2, 4, 3. 2 and 3 has no connection. 2 and 4 has no connection. Sorry, 2 and 4 has connection, but 3 and 4 has no connection. Alright. Yeah, this becomes disconnected. So by removing the vertices 1 and 2, the graph becomes disconnected. Even if I remove the vertices 2 and 5, if I remove the vertices 2 and 5, I hope it is not becoming disconnected. Okay, but what we need is, we need minimum number of vertices to be removed so that it becomes disconnected. Yeah, minimum number is 2, that's it. I'm not saying that removal of any 2 vertices makes it disconnected. We are not saying that. We can find 2 vertices in this graph. By removing it, this graph becomes disconnected. That's what we are saying. Okay, so we say that this graph has vertex connectivity 2. So now let me define vertex connectivity. So we denote with K of G. K of G we mean vertex connectivity. So this is how it is defined. Minimum number of vertices. Let us define. So here you can see the definition of cut vertex. That is a subset of a vertex set, so that G minus V prime becomes disconnected. G minus V prime, it means here you can see the example. Here by taking V prime equal to 1, 5, and you remove these 2 vertices from the graph so that you get G minus V prime, which is here. The graph becomes disconnected. Therefore, I can call this set as vertex cut. And this vertex connectivity is defined for non-complete graphs. For non-complete graph, the definition is minimum number of vertices to be removed so that the graph becomes disconnected. But when it comes to a complete graph, we will take another definition. That is minimum number of vertices to be removed to produce a graph with single vertex. That is what a non-complete graph is. Now let us work on some examples. So does it have any cut vertex? G1, yeah. What are those? Tell me. C is a cut vertex, yeah. How many cut vertices it has? C is a cut vertex, E is a cut vertex. That's it, right? By removing any other vertex, you can't make this graph as disconnected. There are only 2 cut vertices. So CE. B, by removing B, oh yeah, you're correct. B also. B is also. By removing B, we make that A as isolated. it becomes disconnected. Yeah, C, E, B, any other? Removing F, no, G, no, H, no. That's it. Okay, now let me come to the below graph. How about this graph G2? Yeah, C is the cut vertex. Does it have any other cut vertex other than C? No. Okay. So there is no other cut vertex. Only cut vertex here is C. Done. Now similar to the cut vertex, let us define a cut edge. Now let me talk about cut edge. I hope you know the definition. What is cut edge? By removing that edge, the graph becomes disconnected. Okay. So does G1, does it have any cut edge? Yes. If you take the edge CE, so here you take CE, so this is a cut edge for this graph. Any other cut edges? I hope we can have one more cut edge. Yeah. Remember one thing. Okay, fine. Let me write it. So that is A, B. So this is one more cut edge. See, when you cut the edge, the graph, you're just removing the edge. Okay, you're not removing the vertex. Remember that. For example, by removal of EC, this is the graph I'm going to obtain here. By removing the edge EC, this is what we get. Okay, we are not removing vertices. Can we apply all these definitions to diagram? Yes. We can apply all these definitions to diagram also. First, I need to come from path. First, what is a path in a diagram? Okay, we say there is a path from A to some other vertex E if there are directed edges from A to E. I'm saying there are directed edges. I'm not that one directed edge from A to E directly. Okay, so you need a directed path from A to E. Okay, so how about G2? Does it have any cut edge? So when it comes to this graph, you are saying the cut edge are this. All right, fine. So how about G2? Does it have any cut edge? This is cut vertex. No, you remove any vertex here, any edge here, it do not become disconnected. Therefore, it has no cut edge. All right. Even we can discuss about edge connectivity also. Edge connectivity, it means the minimum number of edges to be removed so that the graph becomes disconnected. Like the vertices case, the same analogy we'll take here. Minimum number of edges to be removed so that graph becomes disconnected. So for example, in the first graph, the minimum number of edges is 1. If you remove one edge, it becomes disconnected. That edge is nothing but CE. But in the second graph, by removing one edge, can we make it disconnected? No. So we need to remove minimum two vertices, sorry, two edges. That is, either you can remove AC, BC. Removing these two, this graph becomes disconnected. But if you remove AC and CD, it is not becoming disconnected. Alright. So the edge connectivity we denote with the notation lambda G. Lambda G represents minimum number of edges to be removed to obtain a disconnected graph. Okay, so that is what lambda G. Alright. So edge connectivity. So lambda G for this graph is 1, whereas lambda G for this graph is 2. And similarly here, edge connectivity is 1 here, and here edge connectivity is 1. And if you see the relation between the edge connectivity and vertex connectivity, this is what we can say. This k of G is less than or equal to lambda of G. And this is going to be less than or equal to minimum degree of V, where V belongs to capital V. Okay. So to make a graph disconnected, it is so simple. You just look at the vertex with minimum degree. You remove all edges incident with it. Then the graph becomes disconnected. Okay. Now if you see the lambda G is always less than or equal to minimum of degree V, where V belongs to the vertex. Okay, this is the relation we can say. But I hope these topics are not given in the reading material. Edge connectivity, vertex connectivity. And similarly, there is another concept that is 1 connected, 2 connected, k connected. But anyway, let me move to other things. Let's move to directed graphs now. Okay. So before going to the directed graphs, let us try to see how to identify paths of different lengths. For example, you take this graph. So how would this graph, is it connect? Okay, this is anyway connected. Both are connected graphs only. In the first graph, do we have any cut vertex? In both the graphs, you do not find any cut vertex. There is no cut vertex. Is there a cut edge? Oh, is there a cut edge? What is it in the first graph? BG? How BG is going to be cut edge? No. Okay, if by removing BG, this is the graph you are going to obtain. I hope I can extend it like this so that it becomes a mice, no? Anyway. So this becomes connected by removing the edge BG. Okay, there is no cut edge, there is no cut vertex for this graph. Okay, because you can see the lambda of G or K of G, the minimum number of cut vertices needs to be removed are 2 here. By removing BG, the vertex, I'm talking about vertex, it becomes disconnected. But how many minimum number of edges needs to be removed here to make it disconnected? By removing one edge, it is not disconnected. A is connected to G. Yeah, A is connected to G. So this is I'm actually talking about it's not degree. Okay, this K of G represents minimum number of vertices needs to remove so that graph becomes disconnected. I'm saying those vertices here are, you can take BG. Not only BG, you can take even CF. Even if you remove C and F, these two vertices, the graph becomes disconnected. Now when it comes to edges, I hope you can remove G and B. No, I mean sorry. You remove this edge and you remove this edge so that it becomes disconnected. So connectivity of edge is also 2 here. Okay. So similarly here for this graph, try to identify cut vertices, cut edges, and vertex connectivity and edge connectivity. Okay, I'm leaving it as an exercise. Right. Now let us discuss in terms of adjacency matrices. So let us try to understand adjacency matrix. Let me take this graph 1, 2, 3. So what is the adjacency matrix of this graph? It is 0, 1, 1, and this is 1, 1, 0, 0, 0, 0. So this is the graph A, right? Now you can see that there is 1 at 1, 2 position. It means it represents that there is an edge between 1 and 2. Okay, it means there is a path of length 1 between 1 and 2. That I can say. Similarly, this element represents there is a path of length 1 between 1 and 3. Okay, now let me see A square. What A square represents? A square, it means you know A into A, that is you need to multiply these two. When you multiply these two, what do you get? So the first column is going to be sum of these two columns here. Oh wait. Okay, so this is 2, 0, 0. The second column is the first column, and even the third column is also the first column. I hope I explained column and row multiplication in the class, right? Anyway, you directly multiply if you are not familiar with it. Directly multiply by element and write it. You know row column multiplication, no? You just use it. Right? Now let me look at the entries of A square. The entries of A square is this. Now how these entries are connected with a graph. Okay, so now let me look at the first entry. Here the first entry is 2. Okay, so it is talking about a vertex 1 connected with 1. So what it says is there is a path of length 2 from 1 to 1. From 1 to 1 there is a path of length 2. What is that path? You can go from 1 to 2 and then you can come back 2 to 1. So that is nothing but 1 to 2 and then 2 to 1. So this is a path of length 2. Okay, and now let's see this. There, this represents the element 1 comma 2. No. Now it says that there is no path of length 2 between 1 and 2. It is 0, therefore it says that there is no path of length 2 between 1 and 2. Okay, and even this element represents 1 3 element. So this says that no path of length 2 between 1 and 3. Yeah, you can't go from 1 to 3 in even number of ways. Let's say maximum you can go to 1 to 3, and you can't come back to 3 again using one edge. Do you understand? So there is no path of length 2 from 1 to 3. So that is what it says. Okay, let me look at the other entries. So how about this entry 2 2? So from 2 to 2 there is a path of length 2. Sorry. And moreover there is exactly one path of length 2. And this 2 represents there are two paths. Those two paths are, one path is 1 2 1 and another path is 1 3 1. And this represents actually number of paths. All right. So if you write a power r, okay, and you take ijth entry of a power r. So ijth entry of a power r represents, it gives number of paths from I to r, or number of paths of length r from I to j. Do you understand? So the entries in a power r represents number of paths of length r from I to j. So here the 1 1 entry is 2. It means there are two paths of length 2 from 1 to 1. And you can see that here 2 3 entry, I mean 3 2 entry is 1. It means there is exactly one path of length 2 from 2 to 3 or 3 to 2. Okay. So let us try to see what is a cube here. Now if I compute a cube, that's what a square into a. What is a square actually? 2, I hope 0 0 0 1 1 0 1 1, and this multiplied with what is a? Yeah, 0 1 1 1 1 0 0 0 0, right? So by multiplying these two, what do you get? The first column is sum of these two columns, that is this, and next the first column. So this is what a cube. Now we can say that number of paths of length 3 from, how did I name the vertices? I named vertices as 1 2 3. All right. So from 2 to 3. 0? Yeah. Because you see what is 2 3 position. Where is it? Here. So this is 2 3 position, right? So the 2 3 entry is 0. So the number of paths of length 3 from 2 to 3 are 0. Zero in here. Let's see. Let's look at the picture. I hope I have taken this as 1 2 3. So if you want to come from 2 to 3, you need to travel even number of edges. That's it. You can't travel by odd number of edges. Okay, so there is no path of length 3 from 2 to 3. From the picture, it is very clear. Okay, so this is how, using adjacency matrix, we can find number of paths of particular length. Okay, now let me do one thing. Let me give you one more exercise. A, B, C, D. So now I want number of paths of length 4 from A to B. How many number of paths are there of length 4 from A to B? So write adjacency matrix for it. What is it? A equal to, let me write in this order, A, B, C, D. Okay. So the matrix is, if I take A, B, C, D, so this is anyway 0. A is not connected to B, 0. It is connected to C and D. So 0, 1, 1. And this is B is connected to, it's incident with C alone. And C is incident with A and B. Got it? So 0, 0. Okay. So this is the matrix A. So now we need to find A power 4. So let's quickly write what is A square here. So A square is 2, 1, 0, 0. And the next one is 1, 1, 0, 0. 0, 0, 2, 1, 0, 0, 1, 1. So this is A square. So how about A cube? So when it comes to A cube, sum of this 0, 0, 3, 2, 0, 0, 2, 1. And next sum of us, so 3, 2, 0, 0, 2, 1, 0, 0. And just one step away for finding A power 4. A power 4 is last two. Okay. So that is 5, 3, 0, 0. Third one, 3, 2, 0, 0. First two, 0, 0, 5, 3. And the first one, 0, 0, 3, 2. Alright. So now what is the answer to this question? Number of paths of length 4 from A to B. So A I have taken here and B it is in the second place. So the answer is 3. Am I correct? Okay. Okay, so it is better to learn matrix multiplication via rows and columns, so that this much easily you can write A square, A cube, and A power. Okay, try to see the matrix multiplication in terms of sum of columns and sum of rows. Then things becomes easy. All right. Now there are few more things we need to discuss. Um, I need to discuss about directed graphs and directed paths. As of now, I'd like to stop it here. Okay, so we will continue after a break, maybe 20 minutes break. Okay.